Hello and welcome to our lab on electricity and magnetism. Now the first couple of activities of this lab just deal with magnets. And so most of you are familiar with the way that magnets work. Here I have a cylindrical magnet, and it's just a little red magnet here. It's a cylinder. And I can look at it and I can sort of tell which is north and which is south by bringing it up to a compass. Now a compass needle points to the magnetic south, and so which is geographic north. And so when I hold this magnet near the compass, the needle is going to point to the south pole of the magnet. And so by turning this magnet around, I can determine the north and south pole of the magnet itself. Now once I know the north and south pole, I might need to somehow remember which is which, because that's important later. I want to look at sort of the field, the magnetic field around this magnet. And to do that, I'll put the magnet in this pan, and on top of the magnet I'm going to put a plastic sheet. That's important because I'm going to sprinkle iron filings on top of the sheet. I do not want them to come in contact with the magnet. If that happens, then it takes a long time to pull those individual metal filings off of the magnet and put them back into here. After I'm through observing the field of the magnet with the iron filings, I want to carefully remove the magnet and shake all the filings down and pour them back into the jar and have that ready for the next slab. So don't leave any magnet filings lying around on the table. Make sure any excess is brushed off, because you don't want them to be in contact with your little red magnet. Now after you've looked at the field of the permanent magnet, let's talk about the distance dependence of that field. Now, you probably know as you get further and further away from a magnet, the field of it gets weaker and it's stronger when it's close to it. And so the field drops off. It goes with 1 over the distance raised to some power. And depending on the geometry of the magnet, that power of inverse R is sort of describes how the field falls away, how it decreases or diminishes with distance. So the way we'll determine that is using this magnetic field sensor. Now this magnetic field sensor, I'm going to set it onto the 6.4 millitesla range. A tesla is a unit of magnetism. And the sensor is actually up here. You see this white circle at the end of the sensor? That's actually where the sensor is. And I can turn this, but let me keep it straight for now. And if I set that on the meter stick, I can make distance versus magnetic field strength measurements. Now those distance measurements won't be measured from the end of the magnet, but from the center of it. So to find the center of the magnet, of course, you measure its length and divide by 2. And then wherever that half distance is, I want to put it at some starting point on the meter stick. Maybe I'll put the center of the magnet at the 10 centimeter mark here on my meter stick. And so once I've done that, let me put it up here where we can see it. Then I can make distance, and I measure my distance not to the end of the magnet but to the center, make distance versus measurements and magnetic field strength measurements. And so up to this point, a lot of our measurements have been quantity versus time. Well, these aren't versus time, these are versus, this is versus distance. And so you can change log or pro from time-based data collection to event-based data collection. And there are instructions on how to do that. So you'll plot magnetic field strength and distance from the center of the magnet, and you'll be able to visually see how that magnetic field strength decreases with distance. And so by doing some curve fitting, you should be able to determine the power of R in our 1 over R to the X relationship. So that's activity 2. Activity 3 deals with electricity. Now what I have here is a solenoid. It's many turns of wire around in a loop here, and as it turns out, if you put an electric current through a conducting wire, a magnetic field will be created. Now that magnetic field has a strength that's proportional to current and the distance from the wire that you're measuring, etc. But one way to increase the field strength is, instead of having one wire, to loop it back around on itself, and then it looks like two wires. It looks like twice the current, basically. And so you keep making loops, and that magnetic field gets stronger and stronger and stronger, and eventually we have a really strong magnetic field. So what I want to do is take a look at this relationship between electricity and magnetism, which says if I put an electric current through this wire, there's going to be a magnetic field associated with it. And so in order to measure that, I'm going to look at this with a compass. So I can attach my wires here to the back of the solenoid. The banana plugs fit right in there. And then I'm going to attach this to my battery. You may have some different kind of battery. And I can make a contact here and cause a current to flow through the solenoid. I don't want to leave that contact long, or the solenoid would get hot. I can melt these wires, and of course I can drain the battery. So I just want this to be a momentary contact, 3 or 4 seconds at a time. And then with my compass right here parallel to the tabletop, as I make that contact, I see that sure enough I get a deflection in the compass needle. And as I move this compass around the solenoid like this, parallel to the tabletop, I begin to get a feel for the shape of the magnetic field around that compass. And as it turns out, it looks very similar to the magnetic field around a little short bar magnet that's pointed this way, maybe right through the center. So it's very similar to our cylindrical or bar magnet. Those magnetic fields are going to look very close to the same thing. So you'll sort of plot that. Now in activity 4, we take a look at the inverse of the relationship. In other words, if an electric current can cause a magnetic field to be created in a conducting wire, well, what happens if we have a magnetic field that moves near a conducting wire? Will it create a current? Does it work backwards? And we'll test to see if that effect works backwards by using this galvanometer. Now the galvanometer is sort of like a current meter, but what it reads here is not amps or milliamps. It's not scaled to current, but it just shows a deflection in the needle. A deflection to the right means a positive current, and a deflection to the left means a negative current. And so please do not connect this galvanometer to your battery. It'll slam the needle one way or the other and destroy the galvanometer. This reads very small currents. And so we want to make sure that these wires are detached from our battery. And now with the galvanometer here, I can attach the galvanometer to the solenoid in the same way that I earlier attached the solenoid to the battery, except this time to the galvanometer. And now, here's my solenoid. I'm going to move this cylindrical magnet in and out of the solenoid, and sure enough I get a deflection in the galvanometer. And so looking at the way my wires are oriented, and looking at remembering what's the north and south pole of this magnet, I can start making a prediction about which way current is going to flow in this solenoid based on the orientation of the magnetic field and the deflection of the current needle of the galvanometer. And so as it turns out, yes, a moving magnetic field, not a stationary one, near an electrically conductive wire causes current to flow. So what we explored there in activity 3, we showed that the opposite is true in activity 4. Activity 5 is sort of fun. It says, well, is there some sort of force? Can we see a force, a magnetic force? And here's the idea. If I can make a current flow in this galvanometer, and by doing that, create a magnetic field, and we saw with the compass that there is in fact a magnetic field here, does that magnetic field repel or attract a permanent magnet? And to test that, we're going to attach this solenoid, make sure the galvanometer is unplugged, to the battery again. And so if you'll remember from last time, you kind of know what field is created, whether it's a north pole field or a south pole field, the direction of the field based on your compass reading. And so now you'll hold the cylindrical magnet near the solenoid. Actually, we'll put part of it inside the solenoid where the magnetic field of the solenoid is the strongest and most uniform. And then we'll close the current and see if indeed there is a magnetic force between the magnetic field we create electrically, in other words, the electromagnet, and the permanent magnet. So that's activity 5. So this lab is all about some exploration and getting a conceptual feel for magnetic fields and currents. And I hope you just have a lot of fun with it and learn something about electricity and magnetism.